Hi, this is Billy Mencken, back with another science project edition of Exeter COSMOS 2019. Today we'll be talking about cloud chambers, which allow us to see invisible fundamental particles in a simple, clever way. This video will cover how to build, operate, and analyze a cloud chamber, and will also teach you the types of radiation it will allow us to see. Welcome back. Let's quickly talk about radiation. Alpha radiation is an ejected helium nucleus with a positive charge, travels distances in our atmosphere on the order of centimeters, and cannot penetrate most materials, like clothing, paper, or water. Weighing 6.6 times 10 to the negative 27 kilograms, alpha particles are gargantuan compared to their cousins, beta particles. Beta radiation is electrons and positrons ejected during nuclear decay. These particles, smaller and lighter than alpha particles, are able to penetrate clothing and the top layers of skin. Radon is a radioactive gas present in ambient conditions which emits alpha particles as it decays. And finally, muons are negatively charged like electrons, but much heavier. They are formed as a byproduct of reactions when cosmic radiation strikes particles in the upper atmosphere. Muons interact very little with other particles except through ionization, which you should remember for later. As a fun fact about muons, their half-life is only 2.2 microseconds, which at the speed of light translates to 660 meters. How then are they able to come all the way down from the atmosphere? That's because at relativistic speeds, we perceive muons' lifetimes as much longer. Feel free to research this yourself. Okay, back to cloud chambers. A cloud chamber can look like this, or this, or this, which was ours. To build your own, you'll need the following things, many of which you can hopefully get from school. A glass or acrylic container bounded on all but one face. In our case, we used a glass fish tank with the form of a rectangular prism. You'll need 2 to 3 sheets of felt, preferably dark, glue that sticks felt to glass or plastic, like Elmer's plastic cement, half a cup of 90% isopropyl alcohol solution, 2 blocks of dry ice, and gloves to handle them. You'll need a surface upon which the dry ice will rest. We used a tray from our dining hall. Any black surface, wood or plastic, thin but rigid, and wider than the opening of the fish tank. This will be used as a lid for the tank. We spray painted the back of a whiteboard. You'll need radioactive sources, like maybe lead, a smoke detector, which is built with americium, a beta emitter, etc. We also use neodymium magnets, a Van de Graaff generator, and a white light source that provides a beam of light. Here's that list again. And here's how you build it. First, adhere the felt to the inside of the glass container. Once that's dry, soak the felt with isopropyl alcohol. Then take the dry ice and place it on top of the tray, your base. Take the lid and place it on top of the dry ice, and then take your radioactive emitters and put those on top of the lid. Once that's finished, you can take your glass container, flip it upside down, and put it on top of the lid. Then turn the lights off in the room and turn your white light source on so it shoots a beam across all the radioactive emitters. After 5 to 10 minutes, the whole container will be saturated with alcohol vapor, and charged particles zooming through the container will leave visible cloud tracks. You can observe, take video, and experiment by taking the Van de Graaff and bringing it close to the chamber. Alright, now for how it works. The alcohol in the felt evaporates over time, but some of the vapor at the bottom of the container, near the cold, dry ice, condenses to a visible mist, and some of it reaches a state right on the verge of condensing. That is, the air near the bottom becomes supersaturated, with alcohol on the brink between a gas and a liquid. Charged alpha, beta, and muon particles zipping through the chamber often have enough energy to knock electrons off of atmospheric molecules, ionizing them. The polar alcohol molecules are attracted to these ions and latch onto them, forming droplets. The formation of these visible droplets follows the path of the particle, which we can then see in the cloud chamber. Now for some analysis questions. What different track shapes and lengths did you observe? Through research on the mass, velocity, and energy of alpha and beta particles and muons, can you guess which tracks were created by which types of radiation? What changed inside the cloud chamber when the Van de Graaff was introduced to the vicinity? Give quantitative and qualitative observations. Why did this occur? As a hint, you can think about how the clouds are formed. And a special challenge for the physicists out there: was the magnetic field of the magnet sufficient to curve the trajectory of any of these charged particles? Can you calculate the necessary magnetic fields to curve one of these particles? This will depend on their speed, mass, and charge, which you can find online, and the radius of curvature, which you can set to a reasonable 2 to 5 centimeters. We'll answer these questions ourselves in a few seconds, but first we encourage you to take a shot. Okay, here's what we thought. Particles were identified by their trajectory. Streaks shooting radially from the americium were alpha particles. Streaks without radiating sources were either alpha particles from ambient radon radiation, matching the shape of those coming from the americium, or muons, leaving longer, thicker tracks. Alpha particles emitted from the americium smoke detector were most common. Without the Van de Graaff, they traveled 1 to 2 centimeters, but with it they reached tracks as long as 4 centimeters. In the presence of the electric field caused by the Van de Graaff, the energy required from radiation particles to ionize the air is lowered, like a catalyst. Sometimes, if we brought the Van de Graaff very close, we wouldn't even need charged particles to create clouds, like we're showing here. We saw shorter, thinner, zigzagging tracks upon close inspection. These bouncing particles, which looked like spiderweb, were high-energy electrons and positrons, both formed when cosmic rays collided with air molecules, and also emitted from the radioactive beta source. We observed no curving effect from the magnet, although few particles passed by. Curving an alpha particle in a 2 centimeter radius would require 15 teslas, which is possible only with extremely powerful electromagnets. Alright everybody, that's it for cloud chambers. We hope you try it yourselves, and you could even send us some video or some pictures. Thanks so much for watching, and stay tuned for more Exeter COSMOS videos.